In this question, we're told that figure 1 shows the central vertical cross-section, ABCD, of a paddling pool that has a circular horizontal cross-section. Measurements of the diameters of the top and bottom of a paddling pool have been taken in order to estimate the volume of water that the paddling pool can contain. Using these measurements, the curve BD is modeled by the equation y equals the natural log of 3.6x minus k, as shown in this diagram here. We've been asked to work out a value of k. So you can see from this diagram that when x equals 1, y equals 0, so we can substitute both of them into this equation. So 0 will equal the natural log of 3.6 minus k. And we know the natural log of 1 is 0, so 3.6 minus k has to equal 1. So k will equal 2.6. For part B, find the depth of a paddling pool according to this model. So when x equals this 1, we go to this point. So when x equals 1.18, we'll get to point B. So I'll substitute 1.18 into our equation for y. So y will equal the natural log of 3.6 multiplied by 1.18 minus our value for k, 2.6. So y will equal 4.995. So this will be the depth of a paddling pool. For part C, the pool is being filled with water from a tap. Find in terms of h the volume of water in the pool when the pool is filled to a depth of h meters. So we're going to rotate this curve 360 degrees about the y-axis. So this will be a volume of revolution. And the formula for the volume of revolution about the y-axis is that v will equal pi times the integral of x squared dy. So the next thing we need to do is to make x the subject of this equation. So we'll have e to the power of y is equal to e to the natural log of this. And then the e and the natural log will cancel. So we'll get e to the y will equal 3.6x minus 2.6. Then we'll move this to the left-hand side and divide both sides by the 3.6. So now we have the equation for x. We need to square this to get x squared. So the easiest way to do this is to pull out the 3.6 squared and then have e to the y plus 2.6 all squared. So then we need to expand out this bracket and we get all of this. And then we'll substitute this into the volume of the revolution. So we've been asked to work out the volume in terms of h. So our limits will be from 0 to h. And we can pull this 1 over 3.6 squared in front of our integral because it's just a constant. And then when we integrate each term, this becomes 1/2 e to the 2y. This is the same, and this becomes 6.76y between the limits of 0 to h. So now we'll substitute in our limits. We know e to the 0 will become 1, so this is a half, and this will become 5.2. So this will be the volume of a pool in terms of h. And then for part D, given that the pool is being filled at a constant rate of 15 litres every minute, find in centimetres per hour the rate at which the water level is rising in the pool when the depth of the water is 0.2 meters. So we've been asked to work out the rate at which the water level is rising. And this is the change in height over time, the dH by dt. We have the equation for V, which we can differentiate to get dV by dH. And we've been told here that the pool is being filled at a constant rate of 15 litres every minute. So this is dV by dt. So what we need to do is to put these two together using the chain rule to get dH by dt. So this will be dH by dV multiplied by dv by dt, because then these dv's will cancel. So the first thing we need to do is find dv by dh, and then reciprocate it to get dh by dv. So when we differentiate v with respect to h, we can leave this constant alone, and then we're told here that the depth of water is 0.2 meters. So we can substitute this h into here, and that will get us dv by dh at that point. And when we work this out, we get 3.54 meters cubed per hour. So then we'll reciprocate this to get dh by dv. So now we have this term. To find dv by dt, we need to convert this 15 liters every minute into meters cubed per hour. And we know that 1 liter is 1,000 centimeters cubed. So 15 liters will be 15,000 centimeters cubed. But this is per minute. What we need is per hour. So we'll multiply this by 60. So this will be 900,000 centimeters cubed per hour. But we need it in meters cubed. And we know that 1 meter cubed is the same as 100 cubed centimeters cubed. So we'll divide this 900,000 by 100 cubed, and we get 0.9 meters cubed per hour. So now we have dH by dV and dV by dt. We can work out dH by dt. This will be 1 over 3.54 multiplied by 0.9. And this gives us 0.254 meters per hour. But in the question, it asks for centimeters per hour. So we need to multiply this by 100. So dH by dt will be 25.4 centimeters per hour. Okay. Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the lessons on this topic from my website, mrmathematics.com. I'll leave a link in the description below.